Hi, welcome back to the lecture series on GPU architectures and programming. So, from this lecture onwards, in week 9, we will be moving out of CUDA programming of GPUs, and we will be introducing an alternate programming paradigm which is also fairly useful in the context of GPU programming, and this is what we call as OpenCL programming language. Okay. So, the way we will be making the coverage is that we will be introducing OpenCL as a programming language, but also we need to understand that it has a underlying runtime system. We will look into how the runtime system operates, and the next important thing would be we will be looking into how OpenCL, unlike CUDA, which is useful only in the context of NVIDIA GPUs, we will like to see that how OpenCL being a more kind of open, vendor independent offering, how it is applicable for a wide variety of GPU or GPU like programming computer architectures, and that is why we will see that how OpenCL is specifically suitable for what we call as heterogeneous computing. That means one can write an OpenCL program which can be partitioned and mapped and scheduled on a complex system comprising different computing blocks starting from CPUs, GPUs as well as FPGAs. So, with this background, if we just look back into how the idea of OpenCL came in. So, in the in this time around 1999 to 2000, computer scientists from various fields have already started using GPUs to accelerate a range of scientific applications, and also we know that if I am looking specifically into the case of graphics workloads, then also GPUs were particularly developed targeting those kind of workloads, right? And if you look into this idea of who was the primary vendor for GPUs, that would be NVIDIA around that time, and then people also started to think of alternate programming languages. Around 2002, Zheng Feng from University of Toronto developed OpenVIDIA, and the way CUDA came into the picture was that in 2006 November, NVIDIA launched the CUDA API, which actually allowed you to write a C-like program that would execute on a GeForce GPU. And finally, around 2008, this group, so essentially it is a conglomeration of people coming from different companies, the Kronos group, they came up with the specification of OpenCL, and it was supported by some of the leading semiconductor vendors like AMD, NVIDIA and ARM. So, what is OpenCL? First of all, the full form would be Open Compute Language or Open Computing Language. So, essentially it is a open royalty free standard for portable parallel programming of heterogeneous parallel computing, or portable parallel programming of a wide range of systems like CPUs, GPUs and also other kinds of processors, for example DSP processors, right. Now, the idea is that we have seen how CUDA works. So, essentially you write data parallel kernels and you execute them on GPUs. But just like GPUs have got a way to execute SIMD code, we know that CPUs also have that facility, although at a limited level of parallelism. Similarly, there are also other processors like DSPs who also provide facilities like data parallel program execution. Of course, at a level that is not that much parallelized like GPUs, but the idea was that since this kind of data parallel compute is supported by other architectures also, why not we come up with a specification such that any semiconductor vendor, if they develop drivers which satisfy that specification, then the programs should run as is on those platforms. So, OpenCL in totality, it comprises the definition of the OpenCL language, its application programming interface, the API, the associated libraries and a runtime system, right. The runtime system will manage the dispatching of the code, and the interfacing with the lower level drivers and all that. Also, OpenCL provides language support for C, C++, Python and Java. That would mean that essentially the OpenCL borrows, is essentially the underlying thing is all defined on C, but for the providing somebody the ability to give some high level specifications like from a language which is much easier to understand or easier to in terms of specification. There are OpenCL C++ as well as Python bindings like PyOpenCL, which are also useful for writing OpenCL code, so that one need not write the code at the level of detail that is required if you are writing a OpenCL program in the original C semantics. So, how did really OpenCL come up with? First of all, these comments and things that are written here are not my personal opinions, but they are more like, so I have put in the reference from where I have taken up this idea that how the evolution of OpenCL happened. So, for example, there were a series of events which took place. For example, the company that is AMD got merged with ATI. Now, ATI was famous for creating low cost graphics cards, and AMD brought ATI and created its own line of GPU architectures. In parallel, NVIDIA was also working, and it has come up with already NVIDIA GPUs which are already in the market and have drawn a significant amount of market share from CPUs, because people soon found that these GPUs were useful for running some parallel compute, unlike they were giving much higher throughput with respect to a comparable CPU. But that would also mean that Intel, a CPU vendor like Intel, will like to get people back into their fold by supporting a language, so that if you write a GPU oriented kernel in that language, it will also run seamlessly in the CPU, maybe with a different performance factor. And some other company like Apple at that point of time was also advocating usage of OpenCL. So, all Apple products came with a OpenCL library already built in, so that if you are writing an OpenCL code, that can just run like off the shelf on any Apple system. So, with support from all these major semiconductor vendors, this Kronos group was formed, who kind of develops the specification and of the OpenCL language, and they formulated the basic draft of OpenCL, and also it received support from a significant number of other companies like embedded suppliers like ARM, Nokia, and IBM, Sony, Qualcomm was also one of the supporters, and TI, and there are many others who supports OpenCL. So, when I say there are companies who support OpenCL, that would mean that whenever they come up with a silicon, their own architecture, processor architecture, associated with that, they will also provide a library, a low level library, and the required drivers called the ICD files, using which if somebody is writing an OpenCL program written as per written satisfying the original Kronos specification of OpenCL programs, then that library would support the execution of such a program on the respective platforms. So, this is also a figure which has been borrowed from existing literature, which kind of shows that OpenCL is supported by a diverse set of silicon vendors, system OEMs, middleware vendors, application developers, and due to this huge popularity, it is of course important standard just because of the set of companies that are actually in its support. Now, of course, one natural question would be that I believe there would be two important questions like we always hear about NVIDIA GPUs, AMD GPUs, but we are not that much familiar with OpenCL as a programming language. First of all, the reason is, I would say, since it's a fundamentally C based programming language, and also the specification is a bit more complex. Maybe it's again my personal opinion, writing an OpenCL program using the lowest level C API would require a bit more effort than writing a CUDA program, but then also there are benefits of that, and we will soon see that why the apparent difficulty is not a significant deterrent, because in most cases it is a one-time job. So, somehow it is not significantly popular to naive programmers, but if you discuss this with people, let us say working on embedded processing, there is significant penetration from OpenCL programs, and also there are other vendors who are slowly realizing why OpenCL is important from the perspective of computing with heterogeneous systems. Another second important thing I would say, if you notice that there are also FPGA based companies like Xilinx who provide lot of support for OpenCL. The idea is that it's the way FPGA development works is you would write a program in a hardware description language like Verilog or VHDL, and there would be a synthesis tool, maybe a high level synthesis tool or a normal standard synthesis tool, which will actually compile your structural or behavioral specification written in that hardware description language, and create the corresponding LUT map for the FPGA, right. But the thing is, if when they say that okay, they are also supporting OpenCL, that would mean they provide alternate high level synthesis tools through which if you are writing an OpenCL kernel, it is also compilable and runnable on FPGAs coming from Xilinx. So, that is also an independent workload. So, as we can see that we have one common language through which if I write a SIMD kernel, it can execute on any vendor supported CPU, on any vendor supported GPU, as well as a FPGA like device. So, this would be an alternative way to look at it. So, in the 1990s, the workhorse cross-platform professional 3D apps and gaming, that was OpenGL, and it came up with new extensions to enable desktop graphics capabilities. Coming to 2000s, we had ubiquitous mobile gaming and graphics apps being supported. So, that actually meant OpenGL had an extension, the OpenGL ES 3.2. It was released to bring this AEP functionality to the core. So, they supported all these embedded domains like mobile gaming and graphics apps. And then in around 2005, there was another extension of OpenGL into safety critical graphics. So, that was the extension OpenGL SC. So, it was a separate working group from called safety critical working group, and around 2008 there was this advent of OpenCL as a language for heterogeneous parallel compute, and pretty soon there was this OpenCL 2.0 specification, and associated header files and libraries were released. The headers were decided, and the libraries of course had to be released. They received vendor backing, and around 2014 we had this portable intermediate representation for graphics and parallel compute, and finally something important happened around 2015, which was the creation of the Vulkan API. So, people found that okay, in the mobile world, for writing a data parallel kernel, it is possible to write a OpenCL based data parallel kernel and run it, but maybe it is still not that popular from the mobile developers point of view. And alternate was the Vulkan API, which is a very much OpenCL like language, and it is supported directly in the Android platform. So, this would mean you can have OpenCL code executing inside a mobile system, for which you have to have OpenCL support on the mobile system, which is fairly common if you have a ARM Mali based GPU, or similarly other vendor supported GPUs who also provide the corresponding OpenCL ICD files. However, an alternative way which is a bit easier would be to write the code using the Vulkan API, which is also a very much OpenCL or the original OpenCL like specification for writing such data parallel kernels, and they get direct support from the Android ecosystem. And that is also heavily used nowadays for writing performance critical graphical apps. So, this is what we have been discussing. that in a nutshell, it's a portable heterogeneous computing language. It's open source, it's cross-platform, cross-vendor standard. It can target a wide range of systems starting from supercomputers to embedded platforms, mobile devices, etc. Using it, you can program diverse compute devices like CPUs, GPUs, DSPs and FPGAs, and the same code can be executed on all these devices. That's another very important point as we are trying to make, that you write an OpenCL kernel, you can execute it in any of those devices provided the vendor of that device gives you the support libraries. And it can also dynamically interrogate the system load and balance its execution across heterogeneous processors. Now, this is something important which we need to understand, that if we are considering a heterogeneous system, at any point of time there may be each of the constituent processing elements may be partially loaded. So, from an ideal load balancing point of view, when I submit an OpenCL kernel, it should be able to get an idea what is the amount of load in each of the compute elements and accordingly balance its execution across the different platforms, and that is also a facility which is provided inside the OpenCL runtime system. So, what about the language? Essentially, it's a subset of C99 with certain extensions. It has well-defined numerical accuracy, and of course, a rich set of special math functions. And the usual way is that you can either JIT compile it or you can generate a binary in offline mode. So, ideally, I can have a runtime compilation and execution, or I can generate a offline binary. Both are fine. Now, the last point which we were discussing earlier also, that I can create a compute kernel and I can distribute its threads across different devices. Now, this is something important, since we are coming from a CUDA background. So, we will first need to understand how all the concepts of OpenCL are very much linked up with all the concepts of CUDA. Maybe some of the names get a bit changed. So, the moment we are able to identify what is the correspondence, we will soon understand why they are so similar. The fundamental reason is both OpenCL and CUDA are built with the assumption of a execution model as well as a memory model, or I would say a platform model. So, if you remember how a GPU architecture was generically defined, we said that it comprises a set of multiprocessors, streaming multiprocessors or SMs. Each SM was containing a shared memory L1 cache, and there were a set of special function units, and there were a set of SIMD cores, the scalar processors or SPs, right? And these SPs were actually used to execute the CUDA threads with a basic scheduling unit of warps, right? So, we had a hierarchical arrangement of processors. The basic processors were grouped together to create SMs, and all the SMs together created the entire GPU. That is about the processing part. Regarding the memory organization part, we thought that inside each SM we would have a shared memory and L1 cache, right? And of course, we also discussed that in modern GPUs we also have the shared memory and L1 cache separate units. But the other important thing was a collection of such SMs together had a L2 unified cache, and then there was the global memory, right? And of course, for each thread we can have its own definition of local memory. Now, when we say local memory, there would be two options. Finally, you will have local variables for thread which are private to each of the threads. They will be making use of the subset of register file which is allocated to each thread. So, essentially from each thread's point of view, it will get binding with an SP and a set of registers, right? By SP I mean a scalar processor, that this thread executes on this scalar processor. It has access to this subset of registers from the entire register file for storing its local variables, and if these registers are not enough, then it can further make use of local memory, which is essentially a small part of the original global memory, right? So, that was the memory model and execution model. OpenCL also considers a similar memory model and execution model. So, again the point would be that whenever any vendor is trying to create some silicon which will be OpenCL compliant, he has to ensure that whatever processor architecture he defines, it should have a correspondence with this memory model and architectural execution model, right. Otherwise, it will be difficult to implement the corresponding libraries. Now, coming back to this name correspondence, in CUDA we only had GPUs from NVIDIA, whereas in OpenCL, since it's going to be a heterogeneous compute language supporting a set of devices, we will call everything a device, right. Every OpenCL device, a set of OpenCL devices together create a platform for computation. Inside the GPU, we had SM streaming multiprocessors. In OpenCL, we will call them as compute units. So, we have a OpenCL device, and OpenCL device will contain a set of compute units. Inside each of the streaming multiprocessors of a GPU, we had this collection of scalar cores, scalar processors or SPs, right, and here we will just call them as Ps or processing elements. So, just to recollect, a GPU is replaced by the term device because everything is an OpenCL device. Inside OpenCL device, like GPUs where we had streaming multiprocessors, we will have compute units in OpenCL semantics. Inside streaming multiprocessors, we had scalar processors, we will now have processing elements. Inside the GPU, we had threads executing, a collection of threads were executing. Threads will be called work items. A bunch of threads together was defining a thread block. A set of work items, a set of OpenCL work items would be defining what we call as a work group, right. So, the thread block becomes work group, the threads become work items, and if you remember, we had a set of blocks, set of thread blocks, which together define the entire grid of CUDA threads. The grid is known as ND range. So, grid, block, thread, that was the hierarchy. Here it is ND range, work group and work item in OpenCL. The name global memory remains same. What was called shared memory in CUDA becomes local memory. That means, inside each compute unit, we have a shared memory, which in OpenCL terminology would be called local memory. So, it is local to that compute unit, but it's not local to the processing element. So, it's local to the compute unit. And the original definition of local memory would be called as private memory in OpenCL. Now, in terms of functions, if you remember, for functions we had the following keywords in CUDA. So, we had global, device. So, whatever was a global function becomes the name a kernel function. So, a global was a function which was callable from the host, but executable on the device in CUDA. Here we will be calling it a kernel. So, it's a OpenCL kernel, right, which execute on a device, and a device function means it is callable as well as executable only in the device. In case of OpenCL, such a kernel does not require any qualification, right. Now, coming to variable types, we had constant variable types, that name remains same in OpenCL. So, that would mean a variable which would be only defined once, and its explicit storage space would be the constant memory segment in the GPU. Now, that terminology and idea would remain same. Then in CUDA, we had this keyword called device for variables, which would be defined in the GPU's DRAM. In case of OpenCL, we will have the device on memory, where it will be defined as a device on global memory, where this will be defined with the keyword global. Again, since the shared memory, the name shared memory is being used as a local memory. So, the shared keyword for each CUDA variable gets replaced with the local keyword. So, shared is local and device becomes global in terms of variable names. So, here we have a pictorial view of the OpenCL platform model. So, this is how the OpenCL platform model is conceived, and as I was saying, any vendor who is trying to create a OpenCL compliant processor, data parallel processor, has to conform to this theoretical model, right. So, we identify that there will be a host device which will connect to one or more OpenCL devices, and OpenCL devices, as we have discussed earlier, it is a collection of one or more compute units. Each compute unit will have one or more processing elements, and these processing elements will execute code in a data parallel way. So, or SIMD or SPMD, that is single program multiple data, or like that is the terminology they will use. Now, similar to CUDA program, in OpenCL also we have two main execution units. They are the kernels and the host program. So, essentially the host program will be occupying this host device and it will be orchestrating the execution of the OpenCL kernels in the different other OpenCL devices. So, when you submit a OpenCL kernel using a host program to one of the OpenCL devices, it defines an index space. An instance of the kernel is is a work item and it executes for each point in this index space. So, if you remember in CUDA we had a grid and instead of that we launched a set of thread blocks, right. So, if you see here the grid is now the ND range and inside this we are, instead of launching threads, we are launching these work items. Each work item will execute and try to compute some value for one of the points in this index space, right. Now, the work items are now organized into work groups as we were discussing earlier, right, and by ND range what we mean is the n dimensional index space where the value of n can be 1, 2 or 3. So, in the highest possible dimension we can have a 3 dimensional arrangement of this OpenCL work items. So, this picture is kind of reproducing us the idea of parallel execution of threads and the different OpenCL keyword concepts. If you remember our initial introduction to the CUDA programming language, we showed the arrangement of CUDA threads where the threads are bunched into thread blocks, the blocks are bunched together into a grid. Here we have a similar thing. We are trying to show different possible cases of 1 dimensional, 2 dimensional as well as 3 dimensional arrangement of the index space in the ND range. So, we have a 1 dimensional ND range where we have multiple work groups, each of the work groups are containing work items. Similarly, I can have a 2 dimensional ND range which will contain 2 dimensional work groups and the work groups again will contain the work items arranged in 2 dimensions. And similarly, I can have also a 3 dimensional ND range where the work groups are also packed in 3 dimensions. So, with this basic introduction to the OpenCL execution model, we will end this lecture and in the next lecture we will be continuing the discussions further. Thank you.